Oh no, I, the Emperor Penguin of the Middle Penguin Empire, really needs a new space engine for my fancy Penguin Force One spaceship. But what do I choose? Leopard Seals already tricked me and sold me a warp drive, or at least a fake warp drive, because what it did was it just sent me to hell. I need a real engine that really works. Oh no, what do I choose? Well, Mr. Penguin Emperor, you have a couple options that you can choose. Here are some of them. The solar sail has a large reflective sail that gets pushed by solar radiation pressure, meaning the momentum from the photons that make up solar radiation moves the sail. A good example of a solar sail is the 2010 Icaros. It was the first solar sail that was successfully propelled by solar radiation and the first time that a spacecraft used a solar sail as the primary method of propulsion. The issue with a solar sail is that it might not be the speed that you want exactly. For example, through the Breakthrough Starshot initiative, the Planetary Society has found that solar sails could travel up to 10 to 20% of the speed of light. If you like the idea of the solar sail but want something a little more effective at longer ranges, you could try a laser sail, which is, in theory, it's just a solar sail but with one slight difference. Instead of relying on solar radiation, you instead have a laser installation shoot lasers at the solar sail. The thing is, lasers spread out over distances, so you would need very advanced facilities with massive lenses to be able to properly use them over very long distances. Furthermore, you need a lot of energy. When relying on solar radiation pressure, you rely on the energy of the sun, whereas now, you have to produce your own energy to power lasers. Most often, that would probably be some sort of fusion reactor, but that is not possible right now. The best example of a laser sail I could find was the ISV from Avatar, where they have these giant laser sails on the actual ship, and basically the ship would be shot at with lasers while it was traveling towards Alpha Centauri, and upon arrival, they would use their antimatter engines to slow down. Maybe you want something more conventional, something like a chemical engine. Most of the powerful chemical engines are bipropellant, meaning that they use two propellants. They need a fuel and an oxidizer to start burning. Some are also cryogenic and use cryogenic fuels, which are fuels that are stored at very low temperatures in order to keep them in a liquid state. For example, the second stage of the Atlas V rocket, the Centaur 3, that stage uses the RL-10, which is a liquid fuel cryogenic engine that uses cryogenic liquid hydrogen and liquid oxygen as the oxidizer. The problem with all chemical engines is that you have to carry a lot of fuel and oxygen around. Cryogenic fuels solve this problem greatly by liquefying the fuel to increase storage space, but if you want to get to your destination quicker and without relying on gravity assist or weighting, you might want a different kind of thruster. There is another possibility, the Bussard ramjet. The idea is the very fast-moving spacecraft will scoop up hydrogen from the interstellar medium using this very big funnel. Then, with the collected hydrogen, they compress it until thermonuclear fusion occurs, and that will provide the thrust they need to get to their destination. There are some issues with that. For example, apparently in the local interstellar cloud nearby, there's actually less hydrogen than we believe there to be, so it might be that the Bussard ramjet is not as feasible in the solar system, or perhaps not feasible elsewhere. Another downside to rocket engines are that they're going to kill all the space whales and pollute the space oceans and disrupt the space whale songs. Solar sails would make it so that they're going to block up the space whale migration routes. Space turtles are actually going to eat solar sails because they think it'll look like space jellyfish. This is why we should use electric engines instead. For example, ion engines. Ion engines first ionize a neutral gas to create ions. Then the ions are accelerated with electricity to create thrust. For example, electrostatic gridded ion thrusters. In an electrostatic gridded ion thruster, some xenon atoms or some other few atoms are released into a chamber. Electrons from a cathode hit the xenon atoms. They lose an electron and then become positive ions. Then electric grids accelerate the ions. Since the first grid is positive and the second grid is negative, the electric field between them pulls the ions forward. The ions fly through holes in the grid at very high speeds, up to tens of kilometers per second. A neutralizer adds electrons back by spraying electrons into the ion beam, so that the exhaust becomes electrically neutral. This is done to stop the spacecraft from charging up. Then the spacecraft will get thrust because the fast ions going backwards pushes the spacecraft forward. This is what most people think when they hear ion thrusters. A well-known example is the Dawn spacecraft that launched in 2007 and visited Vesta and Ceres. Next up, we have Hall effect thrusters. An electrostatic Hall effect thruster works by turning xenon gas or equivalent gas into plasma, and then using electric and magnetic fields to push that plasma out the back for thrust. Propellant, usually xenon, is injected into a ring-shaped channel, while a cathode releases electrons towards the anode at the rear. A magnetic field prevents these electrons from reaching the anode directly, trapping them in a circular motion, the Hall effect. As they swirl around, the electrons collide with xenon atoms and ionize them, creating positively charged xenon ions. An electric field between the anode and the channel exit then accelerates these ions outwards at high speeds, producing thrust. A neutralizer adds electrons back into the exhaust so that the ion beam doesn't charge up the spacecraft. Perhaps the best and most realistic option for speed and plausibility. Nuclear engines include a wide range of possible designs and options. However, they are almost entirely theoretical. Despite that, there has been research that has gone into nuclear propulsion. Let's start with the most well-known one. Nuclear pulse propulsion uses nuclear explosions for thrust. This is Project Orion, the first study and design attempt at nuclear pulse propulsion. The idea was that nuclear pulse units, which were basically bundles of fuel, and you can think of it as a bomb, were injected behind the craft, and the craft's giant pusher plate, which was a thick metal plate that was tens of meters thick. The bombs had a shaped charge and propellant material to make the focus blast. When detonated around 20 to 100 meters behind the plate, the blast would create a plasma wave and the shock hits the pusher plate. The plate is connected to a complex system of shock absorbers that pushes the craft forward. The craft will keep doing this as long as it deems necessary. Here's another one. Project Daedalus was a study conducted by the British Interplanetary Society from 1973 to 1978 to create an unmanned spacecraft that could reach Barnard's star within 50 years. Instead of using nuclear fission and bombs like Project Orion, Project Daedalus had a fusion rocket. Pellets of deuterium/helium-3 would be injected into the reaction chamber and would be ignited by inertial confinement using electron beams. For context, inertial confinement fusion compresses and heats targets with fuel to initiate the nuclear fusion process. Anyway, around 250 pellets would be detonated per second, and the plasma created would be directed by a magnetic nozzle. There are a couple of problems with this design, however. Obviously, nuclear fusion is still at its infancy right now, and there actually isn't enough helium-3 on Earth apparently to fuel all this demand. So you would need to mine helium-3 on the moon or Jupiter's atmosphere. In a nuclear thermal rocket, instead of a chemical reaction like in a chemical rocket, the nuclear reactor heats up the propellant and the propellant expands and exits the nozzle, producing thrust. This is one of the most plausible nuclear engines and was almost put into actual service. NERVA, Nuclear Engine for Rocket Vehicle Application, was a program run by NASA, and by the time the program was cancelled, they had already created an engine, the NRX-A6, that was actually ready for flight certification. The program was cancelled due to Nixon's budget cuts during the Vietnam War. In this illustration, we can see some of the ways NASA was planning to use NERVA. A fission fragment rocket is one of the more unique ideas here. Basically, it will use the high velocity particles produced during nuclear fission directly as rocket exhaust. In conventional nuclear thermal rockets, the reactor heats up propellant like hydrogen and the heated gas is expelled to create thrust. In the fission fragment system, however, the split uranium nuclei, the fragments themselves, are allowed to escape the fuel and are guided out back of the spacecraft using magnetic fields. These fragments travel at several percent of the speed of light, which gives the engine a very high specific impulse, hundreds of thousands to over a million of seconds, far beyond chemical or even most fusion engines. Because almost all the fission energy leaves as kinetic exhaust rather than heat, the reactor can run relatively cool and lightweight. However, the design produces very low thrust and highly radioactive exhaust. What that means is, if you want to use this engine, you'll have to make sure you're far away from the space whales, space turtles, and space jellyfish, or else you'll be condemning another species to extinction. There's one more option that I haven't talked about, and that's using antimatter. Let's start with the basic one. First, we can try colliding antimatter with matter in some sort of reaction chamber. Through antimatter, annihilation will create high energy particles like pions and gamma rays, and then we can direct those particles out the back for thrust. Another thing we could try is using a thermal antimatter rocket. Instead of directing the exhaust out the back for thrust, we use the antimatter annihilation to heat up a propellant, like hydrogen. The hot gas expands, and then we expel that through some sort of nozzle out the back for thrust. Finally, there's antimatter catalyzed nuclear fission or fusion. So what happens is, for fission, we use the antimatter directly in the fission process, thus we create larger explosions. Otherwise, we could also do something similar to the nuclear pulse propulsion, where we explode antimatter behind the spacecraft and push the spacecraft forward. Else, we can use it for the fusion process, and then we can use the particles that are generated from the fusion process and eject that out for thrust. Obviously, there are issues with antimatter all over the place. The biggest one is that antimatter, if you're not careful with it, it could probably explode and kill everyone on the planet or something. Another thing is, there's not a lot of antimatter that we can produce right now. And right now, it's very expensive already to produce. So there's a question of how we're going to get enough antimatter to use it. Which is why nuclear fission and nuclear fusion with antimatter was an option in the first place. Because you use less antimatter compared to just using an antimatter rocket. Anyway, here's an example of an antimatter engine I found online. Apparently the ISV from Avatar, the one with all the blue aliens, the ISV uses antimatter engines. That's what they use to slow down as they're approaching Alpha Centauri, and it's also what they use to destroy the tree and to land on the planet.